This is Dr. Joyce Miller again. We're continuing our discussion on pre-lab questions for lab activity 6.1. And just to let you know where we are, we've been talking about light. And light and energy have specific jumps. We call those quantum jumps. So if an electron gets excited, and here we have the hydrogen nucleus and one electron in hydrogen, and it's going around in its normal unexcited ground state is what we call that, and it gets excited, and we're using electricity to excite our electron in lab this week. So it goes to a higher energy level, and it can go to these three different energy levels that we're going to be looking at in lab, because these jumps pertain to the visible spectrum. So if an electron is up here and then it loses its energy and it goes back down to the ground state, it gives off a photon. And the photon in this example, I don't know how well you can see it, but it's a violet color, and so it's got a lot of frequency to it. You can see the wavelengths are short, wavelength being defined as the peak to the next peak or the valley to the next valley. It's the same distance. So it has a short wavelength, a high frequency, so it's energetic. Whereas here we have another example of the same electron but being energized to the third level in the orbital, and so then it goes back down to the second level, and it is giving off a photon when it does that, and it's the red photon that it can be giving off. So if it goes up an energy level, it absorbs a photon or energy, a certain energy level. If it goes down, it gives off energy or emits an photon and gives off light. So that's where we are, and now we're going to go further. We're going to go back to the pre-lab questions, but we're going to solve them in reverse order. So we solved number 4 on the first video, and now we're going to look at number 3. So as I mentioned, we have a diffraction grating, and our particular diffraction grating is 500 lines in 1 millimeter. So a millimeter is very small. It's a millionth of, I'm sorry, it's a thousandth of a meter, And so think about a thousandth of a meter and then dividing that up 500 lines in that thousandth of a meter. So our example, though, that we're going to solve has grating that has 750 lines per millimeter. So what's the split spacing? So that's how big are the spacings in between those lines on this particular diffraction grating. So it says to show the work provided and express your result in microns or micrometers. So first of all, we need to think about dividing that 750 lines up in 1 millimeter. So let's do that. So we have the example has us use delta X for our actually D for our slit spacing. So D, little d, equals 1 millimeter divided by 750 lines. And so that's going to give us a number in millimeters. So you can solve that. Take 1 millimeter and divide it by 750 individual lines. And that's our little d. So once you get that number, though, it asks us to express our results in microns. So we need to change that to microns. So we can go through meters to do that. That's the longer way. If you know a shorter way, that's fine. There is a shorter way. So we're going to take, we're going to multiply and get rid of our millimeters. So there's 10 to the third millimeters in 1 meter. So that will get rid of our millimeters, but now we want to end up with microns, so we have to take the conversion factor for changing, I'm sorry, that should be meters. 1 meter. So we need to use our conversion factor between meters and microns. So 1 meter is 10 to the 6th microns. So that's a 6. So there's 1,000,000 microns in 1 meter. So we cross through the meters, and we've already crossed through the millimeters. So our answer, when we divide 1 millimeter by 750, we will end up with millimeters, and then we're going to convert those to microns. So we'll end up with our answer in microns, and that's how you solve that. It would be number of microns. So that is our diffraction split spacing, and that's our little d for that problem. Now let's go to number 2. So now we have assuming visible light of an unknown wavelength shines on a 2-slit aperture. So remember, light can have constructive interference or destructive interference as it passes through slits. Your lab manual and your textbook talk about that. So we're going to have a resulting interference pattern, and it's going to be captured on a screen. And why is that doing that? It's going to be located 3 meters from the aperture. If the fringe spacing is 0.3 centimeters, what's the wavelength of the light in nanometers? So show your work in the space provided. So now we need to use an equation, and that's found in our lab manual, and that is on page 160, and that's equation 1. I don't know why this is being so sensitive. So here is our equation. Delta x equals lambda times capital D divided by little d. So let's write that equation, and then we'll figure out what we're going to plug in. Delta x equals lambda times capital D divided by little d. Now I told you in the first video what those different symbols are, so let's go over those. So little d is the slit spacing, and that's what we found in the example we had in our previous example, number 3, but it tells us in this problem that that is 0.5 millimeters. So that's our value for that. Now our lambda is our wavelength, and that's our unknown. However, we do know something about that because it tells us it's visible light. And so from problem number 4 on the opposite side, it told us that visible light is in the 400 to 700 nanometer. So we're going to check our answer and make sure it's in that range because it tells us to find the answer in nanometers. So once we have an answer, we're going to double check and make sure it's in that range because it's visible light. It's what's told in the problem, tells us that. Okay, so then we have the delta x is part of our equation, and that's the fringe spacing. It's also called the relative displacement, and that's what you'll be measuring in lab, and that is given to us as 0.3 centimeters. 3 centimeters. Okay, and then part of our problem is the capital D, and that is the distance between the aperture and the viewing screen. So that's the distance between aperture and viewing screen. And it's given to us in the problem is that it is 3 meters. So now we see we have our little d is 0.5 millimeters, our delta x is 0.3 centimeters, and our capital D is 3 meters. So we're finding our lambda here. So let's rearrange this problem first of all so that lambda is by itself. So that would be, we multiply both sides by the little d and divide by the capital D, and so we have delta x divided by little d, no, times little d, times little d divided by capital D equals lambda. So that's the equation we're going to use. However, we want it in nanometers, and none of these are in nanometers. So let's convert them to nanometers before we plug them into our equation. So we're going to have nanometers times nanometers divided by nanometers. So we'll end up with the right unit, nanometers. Nanometers times nanometers divided by nanometers gives us nanometers. So let's convert 0.5 millimeters to nanometers. So we can once again go the long route, which is okay, and go through meters. So 10 to the third millimeters in 1 meter, and then we want nanometers, so 1 meter is 10 to the 9 nanometers, and you're going to get an answer in nanometers for that part, for little d. So that goes there in our equation. And then our fringe relative spacing, I should say, it's also spacing, or relative displacement. It's 0.3 centimeters. So once again, we can go through meters. It's the long way, but it's probably more certain until you get used to all these conversions, unless you're already used to them. So we want to get rid of centimeters, so I'm going to put centimeters down here. And there's 10 to the negative 2 meters in 1 centimeter. And then I want to convert meters to nanometers, so that's 10 to the 9 nanometers. Now you might think, why didn't you put 10 to the 2 centimeters over 1 meter? Could have, no problem doing that. So now you're going to get an answer in nanometers, and that is our delta x, so that goes there. Okay, and then we're going to solve for d, 3 meters. That's a little bit easier. 1 meter, and then we have 10 to the 9 nanometers. So we're going to end up with nanometers. So you're going to have an answer here, here, and here in nanometers. So you just need to plug d, this answer in for d, the little d, this answer in for delta x, and this answer in for capital D. And what will you find? You will find the particular wavelength of light, and when you get an answer, double check to make sure it's in this range, 400 to 700 nanometers. It will be. Okay, so let's do number 1. I think this is one of the more difficult ones, if not the most difficult ones of our pre-lab, so that's why I put it off. Okay, it says hydrogen emits 4 wavelengths in the visible spectrum: violet, blue violet, green, and red. By the way, you might not see all 4. That violet one is rather difficult to see. You may see it or may not when we actually do the lab. Use equation 1 to predict the relative displacements of the emission lines in the hydrogen emission spectrum. So let's go back and see if that concept makes sense. We've talked about that, but let's revisit that from our first video. So what that means are relative displacement or fringe spacing. I think fringe spacing is kind of a weird way to think about it. I like the term relative displacement better. So those wavelengths are going to show up suspended in air when we look through our diffraction grating in these areas here. And there's also going to be the same colors over here. And so you're going to measure using the meter stick where those show up from the center of the meter stick, which is going to be displayed on the 50 centimeter in our meter stick. So that's what we're solving for in this problem, is how far away would those different wavelengths be, given some information that's not in the problem. So that's why this one's so difficult. I'm giving you some details here that's not in the problem. So it doesn't tell us what unit to have in the final answer. So let's choose centimeters, because our meter stick is in centimeters. So this is be 40, so that would be from the 50, so that'd be 10 centimeters and 11 centimeters, 12 centimeters. So we could do it in millimeters, but we'll just do it in centimeters. So let's use equation 1, which is delta x equals lambda times capital D divided by little d. Now it tells us to use the visible spectrum, so we should have already found those answers from number 4. So here are the answers, that the wavelengths you're going to use. So you're going to relative displacements of the emission line, so that's 4 of them. So this problem is rather more involved, and I'll go through one of them and then you can do the others. So one of our wavelengths, we'll call this wavelength 1, equals 410, and that's nanometers. Wavelength 2 equals 434. These are given to you. This is about hydrogen. It tells us hydrogen, so that's why we know what these are. Wavelength 3 equals 486 nanometers, and wavelength 4 equals 656 nanometers. Now remember what these values are. That's very, very small. That's a billionth of a meter. And so we're talking about the wavelength. So that's the distance between the peaks of the light. We don't see actual wavelength. We see colors. That's how our brain interprets these wavelengths. So there are different wavelengths or different colors. So we're going to interpret what we see from the displacement, and we're going to figure out what wavelength those are by using this equation. But this particular problem has us do it the other way. It says we know what the wavelength is, so where are we going to find it on that meter stick? So some things that it doesn't tell us, so let's assume the same numbers so that we'll all be together. So it doesn't tell us what the little d is, the slit spacing. So because we're using the 500 lines per millimeter, we're going to find that particular line spacing for this problem. So 1 millimeter divided by 500 equals a certain split spacing, and so that's going to be d equals d, and that equals a certain number. So let's go ahead and solve that. 1 divided by 500 is 0.002 millimeters. Okay, so that's d, little d. Now let's look at capital D. It does not tell us what capital D is, so I'm going to assume that we're 50 centimeters from the light. So I'm going to assume that our distance from the aperture to read is 50 centimeters. And that's realistic for what you're actually going to be doing in lab. So these two values are going to make sense in the lab if we use those same values, and we are going to use those probably. So, so that's what we've got, and we want to probably look at everything in the same units, and we said we were going to solve for delta x in centimeters. In centimeters. So let's solve the first one for the 410. So our wavelength is 410 nanometers, but we want to change that to centimeters. So we're going to go through meters. So 10 to the 9th nanometers in 1 meter, and we want to turn it into centimeters. So 1 meter is 10 to the 2 centimeters. So this is a 9 and this is a 2. So cross out the meters, cross out the nanometers, and we're going to end up with centimeters. And we're going to end up with, let's see here, 410 times 10 to the negative 7 centimeters. So that's going to be our, oh, I didn't put down what that is. That is our wavelength. Okay, so now we have wavelength. We have capital D, but we've already got that in centimeters, so that's okay. We're going to use that. And now we have our slit spacing in millimeters, so let's turn that into centimeters. So let's go through meters. It's okay. So 10 to the 3 millimeters in 1 meter times 1 meter and 100, or 10 to the 2 centimeters. So that value is going to be 0.0002, nope, one more 0. Centimeters, or let's see, 1, 2, 3, 2 times 10 to the negative 4 centimeters. Okay, so that is our little d. So little d equals that, lambda equals this, and capital D equals that. So now we can plug it into this equation. They didn't give us enough space, did they? So we're going to solve for delta x, that's our unknown, and that's going to be in centimeters. So now our lambda is in centimeters, 410 times 10 to the negative 7 centimeters, times our d, which is in 50 centimeters, divided by our little d, which is 2 times 10 to the negative 4 centimeters. So centimeters, centimeters, and we'll end up with centimeters. So 410 times 50 divided by 2 times 10 to the negative 4. So I should have said 4 times 10 to the negative 7. So let me say that again. 410 times 10 to the negative 7 centimeters times 50 centimeters divided by 2 times 10 to the negative 4 centimeters gives us our answer for the 410. So you'll probably use the other side to do the other values. So you'll do the same thing, but use 434 nanometers, 486 nanometers, and 656 nanometers. So because there's lots of answers to this, I ask you to please circle your answers for that. So this would be a delta x for 1, and then you'd have another delta x for 2, etc. So that covers everything. So you can always email me if you have questions. See you next week.